Okay, so let's recall that a function f is continuous at a number a, given that f of a is defined. F of a is defined. The limit of the function f at a exists, and the limit is equal to f of a. Okay. So those are the conditions for f to be continuous at a number a. And we say that f is discontinuous at a number a if f is not continuous there. Also, we say that a function f is continuous on an interval I if f is continuous at every single number inside of I. Okay, so, and also we looked at what it means to say that f is continuous at a point from the right or left. So let's look at that. So we say that a function f is continuous at a number a from the right if the limit of if the right hand limit of f at a is equal to f of a. Okay, and similarly you define what it means to say that f is continuous at a from the left side. Okay, so those are the basic terminologies that we talked about last time, together with many examples of on this topic. Remember, we said that if I say that f is continuous on a closed bounded interval from a to b, it means that f is continuous at every point inside of that interval, and also f is continuous at a from the right side, f is continuous at b from the left side. Okay. And when that's the case, we will say that f is continuous on that interval. So, for example, this function that I have here, this function is continuous on the closed bounded interval from 0 to 1. At 0, it's continuous from the right. At 1, it's continuous from the left. Recall that we have this theorem which says that if you have two functions f and g, and they are both continuous at a number a, and c is a constant here, then their sum, any multiple of them, or their product, these are all continuous at a as well. So if f and g are continuous at a, all these functions are continuous at a as well. Also, the ratio is continuous at a as long as the denominator doesn't vanish at a. And okay, so one of the new property that I want to give you here, let me use a green color here. For any positive integer n, the function f of x to the n is continuous at a. So if f is continuous at a, then any power of f is continuous at a as well. In fact, number 3 is really, if you think about it for a second, number 3 is basically a version of this guy. If f and g are continuous, f times g is continuous at a, right? Well, instead of taking g, if I take f times f, right, then f times f will be continuous at a. F times f will be f squared. And then you can say f squared times f, which will be f cubed, right? All those powers of f are just products of it. You multiply, what is f to the n? F to the n, you multiply f with itself n times, right? So just by using this, we know that this would be, number 3 is true as well. So any power of f would be any power of f where the exponent is a positive integer, it would be continuous at a as well. So using these 3, I can say that a polynomial, remember, a polynomial function is continuous everywhere. And if I have a rational function, then a rational function is continuous on its domain. So if a is in the domain of the rational function, then the rational function will be continuous at a. Okay, so that's all that we did before Thursday. So I want to continue from there. By the way, any questions, anyone? Okay, so here's an example. Let's say determine where this function 3t plus 2, determine where this function is continuous. Let's actually give this a name. I don't know, maybe call this f of t. So determine where this function is continuous. So this is a root function, the even root of 3t plus 1, 3t plus 2. First of all, so let's let a be any real number, okay? If a is not in the domain of f, if a is not in the domain of f, then f is not continuous at a, right? Is that clear? A is not in the domain of f means what? F of a is undefined, right? So f is not continuous at a. Now let a to be in the domain of f. Well then, recall when we talked about limits, how did we take the limit of a root function like this? So a is in the domain means f of a is defined, right? F of a is defined. So if I take the limit as x goes to a of the function f of, not x, sorry, I'm using t, I guess. We are using t. So what's the limit of this guy as t goes to a? Well, that's the limit of the root function 3t plus 2, and because this quantity is defined at a, how do I find the limit? When we talked about limit, we said when we have roots like this, we can take the limit inside, right? So we take the limit of 3t plus 2 as t goes to a, and then we take the root of that, right? So we can take the limit inside as long as that quantity makes sense for a, right? And what is that limit then? Well, that's 3 times a plus 2, right? And basically, if I have a root function, I can just plug in to find the limit. That's what we saw before, and this is exactly the same as f of a. So what does that mean? It means that if a is in the domain of the root function, that implies that f is f is continuous at A. F is continuous at A. So then I could say, well, what's the domain of, so if I want to know where this function is continuous, I have to find only the domain. So what's the domain of this guy? We know that f is this, right? So what is the domain? It's everything to the right of negative 2/3, right? How did I come up with that? Inside the root, 3t plus 2 needs to be what? Non-negative, which means 3t has to be greater than negative 2, and then finally t has to be greater than negative 2/3, right? So the quantity inside the root is non-negative when t is larger than negative 2/3. So that's why that's the domain. And so we could say that this function that I have is continuous on its domain, which is negative 2/3 to infinity. Okay, so this root function is continuous basically on its domain. Is that generally true? And the answer is yes. If you have a root function, it is continuous on its domain. Okay? So here's here's what I want to say. Recall that the limit of a root function at the limit of a root function g of x at some number a in the domain of the function can be found by just plugging in a for x, i.e. it means that the limit as x goes to a of g of x is equal to g of a, as long as g is a root function and a is in the domain of the function. So altogether what it implies that a root function is continuous on its domain. And now I keep saying a root function, but when I say a root function, I don't mean a function like this. So if I have this function root x, if x is let's say non-negative, and the function is let's say x minus 1, if x is negative, this is not a root. This is not the type of. This is not a root function. Okay? This is a piecewise function. So when I say root function, I'm not including the piecewise functions there, even if the individual parts in the piecewise are root functions. Am I making sense? Okay, so this is not a root function, but this guy is continuous where? Where is this guy continuous? Well, if you think about it, when x is just think about when x is just positive. When x is positive, the function is only given by root x, and root x is continuous on its domain. So when x is positive, the function is f is continuous. When x is negative, the function is given by a polynomial. So when x is strictly negative, the function is continuous as well. Okay. However, when x is exactly 0, in this case, then this guy is not continuous. So you have to check what's happening at the breaking point. So you're breaking the definition of f at 0, right? So on the right side of 0, because the function is given by only this, when x is positive, the function will be continuous there. Same way, it's continuous when x is negative. But when x is exactly 0, what happens? Well, in this case, notice that the limit of the function as x goes to 0 from the right is what? When x goes to 0 from the right, I'm going to use, it means that x is going to 0 from the positive side. I'm going to use the first formula for f, and the limit would be what? 0. And what's the limit as x goes to 0 from the left of this function? Now I'm going to use the second formula. It's going to be -1, and they are not equal. So this function is discontinuous. This is discontinuous at x equals to 0. But otherwise, it's continuous everywhere else. Is everybody okay? So even though, notice that in this case, 0 is in the domain of the function, right? 0 is in the domain of the function, but the function is discontinuous there. Okay? So again, when I say root function, I mean a function given by one formula, one algebraic formula. Okay? All right. Here is a theorem. The function sine x and the function cosine x, they are both continuous. They are both continuous on the entire real number line. I can give you a rigorous proof of that, but I won't. But it should be intuitively clear to you. Those of you who, you should know the graph of sine x and cosine x. If you look at the graph, it is continuous everywhere, okay? But that's not really a proof. Just there is a rigorous proof why these are continuous, but you can just assume they are. Now, once I know these are continuous, how about the tangent function? If I look at the tangent function, right, and I want to know where is this function continuous, how would I come up with that? Well, we know that the tangent is sine over cosine. And what we are going to use is we are going to use this algebraic this theorem that we had. Where is that? Right there. If f and g are continuous at a, then their ratio is also continuous at a, as long as the denominator doesn't vanish at a, right? So that's the one that we're going to use here. So here the numerator is continuous everywhere, the denominator is continuous everywhere, right? So the ratio will be continuous everywhere except where the denominator vanishes, right? The ratio will be continuous. The numerator is continuous everywhere, denominator is continuous everywhere, so the ratio will be continuous everywhere except where the denominator vanishes. So all I have to do is figure out where the denominator vanishes here. Well, cosine x is 0 when? Cosine x 0 is when what? When x is what? And I can keep saying and. So basically, whenever the angle is plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and I can keep going. So as long as x is a multiple of, x is an odd multiple of pi over 2. As long as x is an odd multiple of pi over 2, cosine x will be 0. So tangent is continuous everywhere except at these points, right? Except at these points. There are infinitely many points where it's discontinuous. In fact, this point, what's the domain of tangent? The domain of tangent is all values of x except for these numbers, right? So tangent x is continuous on its domain as well, right? What's the domain? Domain is everything except for odd multiples of pi over 2. And that's true for all trig functions. All trig functions are continuous on their domains. Secant, cosecant, all of them. So if you know their domains, you know where they are continuous. Okay? So all trig functions are continuous on their domains. Is everybody okay with what I said? Okay. If you know the domain, you know where the trig function is continuous. Again, RK means a remark, okay? RK means remark. Here's a theorem. If G is continuous at C, some number C, and F is continuous at the number G of C, then the composition of F and G, the composition function is continuous at C. So if the inside function of the composition is continuous at C, the outside function is continuous at G of C, then the composition is continuous at C. So that's what we are saying here. So here's an example. Suppose I have h of t to be cosine of 3t plus 4. Okay. Where is this function continuous? This is the composition of two functions, right? Here, what's the outside of the composition? Cosine of t, that's the outside of the composition. And the inside of the composition is 3t plus 4. So this is the outside of the composition. Notice that the inside of the composition is continuous on where? Because 3t plus 4 is just a polynomial in t, so it's continuous everywhere. We saw that cosine t is continuous on everywhere as well, right? So where is the composition continuous? the composition would be continuous everywhere as well. So this is continuous on everything. Is everybody okay with that? Here's another example. What if I take the function sine of root of 3t plus 4 plus 2? Where is this function continuous? Well, what's the inside now? The inside is this function, and outside is the sine function, right? And notice that now the inside function is continuous where? Its domain, right, which is negative 2/3 to infinity. That's where it's continuous. The outside function is continuous where? Everywhere. Okay, so the composition will be continuous where? The composition will be continuous. The composition will be continuous on, negative 2/3 to infinity. Okay. Let's look at another example. Let's look at let me think for a second. I want to come up with a let me use this example here. Let's take this function h of x. H of x is given by 1 or 0. It's given by 1 when let me see. It's given by 1 when t is positive. Sorry. When x is non-negative, it's given by 1, and it's given by 0 when x is negative. Okay, when x is negative. And let's think about the function given by f of x, which is the value of the function h at x squared plus 1. So the function f is the composition, right? The function f is the composition of h with x squared plus 1, right? The inside is x squared plus 1, outside is h. H is known as the Heaviside function. You guys in engineering and other applications, you might see this function there. Okay, it's called the Heaviside function. I want to know where is this function continuous. Okay, I want to know where this function is continuous. The inside function is continuous everywhere, x, because that's the polynomial, right? The outside function is continuous everywhere except where? Except at 0, right? The Heaviside function graph looks like what? And the graph of that looks like the following. And maybe I'm going to use so the graph is like this, and then I have a hole right here, right? and this is the height at 1, right? That's how the graph looks like. And so this Heaviside function is discontinuous at 0. So where is the function f continuous? Where is the function f continuous? The function f will be continuous for all values of x for which x squared plus 1 is not what? Is not 0. This guy will be continuous at all values of x except where x squared plus 1 is 0. However, notice that x squared plus 1 is never 0. It's at least what? It's at least 1. So notice that in fact in fact I can say that this function f is continuous everywhere, right? It is continuous everywhere, even though individually the outside function is discontinuous at 0. However, when you're taking the composition, the inside is never 0, so you never have to look at the outside at 0. Okay? So it's continuous everywhere. And in fact, what's the graph of this function f? Can someone tell me what's the graph of this function f? Well, think about this. The function f is h of x squared plus 1. X squared plus 1 is always, you said, is always positive, right? Strictly positive. And what happens when you evaluate h at a positive number? What do you get? 1, right? The Heaviside function, when the input is positive, the value is 1. When the input is negative, the value is 0, right? So in fact, the function f is always 1, isn't it? No matter what x, for any x. For any x, the function f is always 1, isn't it? No matter what x is, x squared plus 1 is positive, so h at a positive input is always 1. So what's the graph? It's just a straight line at height 1. Everybody's okay with that? So that's the graph of f. Is everybody okay? Alright, let's tweak it a little bit and define a different function. It's still using the Heaviside function. So let's look at part B of the question. Let's define g of x to be still the Heaviside function as the outside, and inside, instead of having x squared plus 1, I am going to take x squared minus 1. What's going to happen now? Still the inside function is continuous everywhere. So outside is continuous everywhere except at 0. Right? Except at 0. So together the composition will be continuous everywhere where the inside is not what? Where the inside is not 0. So I have to figure out where the inside is 0. Well, inside is 0 where? When x is 1 or negative 1. So this is continuous on negative infinity to negative 1, negative 1 to 1, 1 to infinity. And also let's figure out the graph of this function. How does the graph look like? Here's one axis, here is another axis, here's 0. Let's figure it out. Let's say negative 1 is right here, okay? That's where negative 1 is, and that's where positive 1 is. What's the value of g at negative 1? What's the value of g at negative 1? When x is negative 1, x squared minus 1 is what? 0. What is h of 0? H of 0 is H of 0, you go back to Heaviside function, right? H of 0 is 1, right? H of 0 is 1. So I know that the value of the function at -1 is 1. Same way, the value of the composite G at 1 is 1 as well, okay? Is everybody okay with that? Okay, between -1 and 1, is x squared minus 1 positive or negative? If x is here, if x is between -1 and 1, x squared minus 1, is that positive or negative? When x is between -1 and 1, x squared minus 1 is negative, and h evaluated at a negative number is 0. So for any of these values, I know that the graph is in between. And I should be careful, I have a hole right here, right? So the graph so far is that. Now, outside of -1 and 1, when x is either bigger than 1 or less than -1, what's the value of x squared minus 1? Positive? Everybody's okay? So when x is outside of this interval, x squared minus 1 is positive. In that case, the value of h is what? 1. So I know that the graph will be given by this here, including, of course, those two dots here. So that's how the graph of G looks like, okay? So this is the graph of G of x. And of course, it's discontinuous at -1 and 1. Okay, so that's that. Here's another, let's see, theorem. If f is continuous at some number b, and the limit of some function g of x as x goes to some number a is b, then what's the limit as x goes to a of f of g of x? Well, you can just find f of b. That is, if you have the composition of two functions, and if you know that the outside function is continuous, then how do you find the limit of the composition? Well, just take the limit inside. Just take the limit inside. So the limit of g is b, and that's what happened. So here's an example to illustrate that. Suppose I take the limit as x goes to 1 and sine of 1 minus root x divided by 1 minus x times pi. So I have to take the limit of this function as x goes to 1. Notice that my outside function is what? My outside function is sine x, and sine x is continuous everywhere. So how do I find this limit? Well, because my outside is continuous, okay, all I have to do is just take the limit inside. So if the limit of the inside exists and the outside function is continuous there, you can just find it by this way. Limit as x goes to 1 of 1 minus root x over 1 minus x times pi. Again, you could do this if whatever the limit of the inside is, the outside is continuous there, if that's the case. Okay, what's the limit now? What's the limit of that quantity? How would I find it? How would you find this limit? Anybody? When you plug in 1 for x, what do you get? 0 over 0. If you get 0 over 0, what's the trick? Either factor out. If you cannot factor out, you rationalize, right? Because you have roots there, you can rationalize like what? 1 minus root x over 1 minus x. I'm going to write the pi at the beginning here. And then I'm going to have to multiply by 1 plus root x over 1 plus root x. I could have factored it out as well, but I'm going to follow this. Okay, what do I get now? When you multiply 1 minus root x and 1 plus root x, what do you get? In the denominator, I get 1 minus x times 1 plus root x, right? When I multiply the numerators, what do I get? Yeah, if you multiply out the two numerators, you'll get exactly 1 minus x. And then you could see that they cancel out like this. And now if you plug in x equals to 1, if you plug in x equals to 1, what do you get? Pi over 2, and what is sine pi over 2? 1. And we are done. Is everybody okay with that? Example. Suppose I have the function root x divided by x squared minus 1. The question is, where is this function continuous? Where is this function continuous? How would I determine that? First of all, let's look at the numerator. The numerator is root x, right? And the root x is continuous where? From 0 to infinity, right? At 0, it's continuous from the right only. The denominator is continuous where? By itself, the denominator is continuous everywhere, right? The denominator is continuous everywhere. However, together, I should only consider the positive values of x, right? Because the numerator is only continuous from 0 to infinity. However, should I include together this guy, so I could say this guy is continuous on 0 to infinity, because both the numerator and the denominator, both of them are continuous from 0 to infinity, right? So the ratio will be continuous everywhere from 0 to infinity except what? Except where? Except where the denominator vanishes, right? And the denominator vanishes when x is what? -1 or 1. So I know that my function root x over x squared plus 1 is continuous on 0 to yeah, I don't need that -1, sorry. 0 to 1 and then 1 to infinity. In fact, that's the domain of that function, okay? Right? How would you find the domain of this function? Exactly the same way. Is that making sense? So that's the domain as well as that's where the function is continuous. 5 minutes, huh? Well, I'm going to make a remark here. Suppose that I have continuous function on a closed and bounded interval. So this is 0. So let's say I have, let's let f of x be a continuous function on a closed bounded interval from a to b. Okay, what does it mean graphically? Let's say I have the number a here, and this is the point on the graph of f corresponding to a, and let's say this is b, and that's the point corresponding to b. So this is the point b, f of b, and this is the point a, f of a, right? So if the function f is continuous on this interval from a to b, graphically what it means is that I can trace the graph of f from this point to the other point without lifting my pencil. I can trace the graph of f from a to b without lifting my pencil. That's what it means to say that f is continuous on that interval, graphically. Okay, I'll stop here. I still have one more topic to go over.